Do you know that it's like the carrot, whatever. If you have a notation ABCD, look like that. Did you see that? This is not a common E, right? This is very scramble. I don't know how to say that. This means time is changing. If I write down E, means I don't consider time. If I write down this one, means this is a function of time. Okay? Are we clear? Okay. If I write down like this way, B, D, H, E, those are all the function of time. They are changing according to time. Okay? For details, you have textbook, you can read. Okay? This is the notation they use in POSA. So, okay. When I say B here is related to magnetic field. I said that, right? Because the definition of B is what? It is the magnetic flux density. What is that magnetic flux density? And also, I say D is electric flux density. It is, just look at the equations. It's simple. B is equals to mu0 times your H field, your magnetic field. Magnetic field is the same, but when the magnetic field it is in different medium, there are some things related to medium. If your electric field is in the air, so you use epsilon 0 and mu 0. This is the notation, the parameters you use to define where is your medium. Okay? So if your H field is in the air, your magnetic flux density B equals to mu 0 times H. If your electric flux density is B, is equals to your E field times epsilon 0, if that is in the air. Those are just constants. Constants. For the air, is mu 0 is 4 pi times 10 to the minus 7. For the epsilon 0 is 8.854 times 10 to the minus 12 for the air. So this is the relationship between E field and the flux density, E and H and their flux density. Okay? So, come back here. You can see here. B is mu 0 times H, right? D is epsilon 0 times E, okay? So E, H. E field becomes something related to H field. E field becomes something related to H field. Okay, they are changing in different sides. In the equation, but here come here, and here come here. Okay? That's why I say E field and H field, and this is the source of the magnetic field, and this is the source of the electric field. And when do we use mu zero, and when do we use epsilon zero? When? If this is in the air, you use epsilon zero, mu zero. If this is in other materials, you use other material. Like if in FR4 board, what is epsilon R? 4.3, right? Epsilon R4. You use this one, which means the epsilon equals to 4.3 times epsilon 0, which is, okay, so epsilon will become this number. This is what we are doing for the FR4. So epsilon R is the constant. You times epsilon 0, you will become the result. What's that? We call that permittivity. Okay. This is permittivity. This is epsilon permittivity. And the mu is permeability. Very similar. Mu and epsilon, they are all the constant related to what material you are using. We will have more discuss about this, but this is very simple. At the beginning, you know what the material is, you change mu and the epsilon, then you know the flux density by using these two equations. Okay? So, after you know this is in the free space, in the perfect vacuum, or maybe air, sometimes we will use this number. The air is a little bit changed, but very similar. So use mu 0 and epsilon 0. And yeah, I think I have some real time. I will explain more about the Maxwell equations. Probably many of you will have a question, why do I need to believe you? Why? Why Maxwell equation? You say it is true, but I never heard it about the Maxwell equations, about these 4 equations. Why? So I try to explain, I try to prove Maxwell equations. This is by experiment. You want to say experiment in Chinese? Yes. And the measurement, the result about experiment. So we try to, for this one, okay, let's focus on these two. Okay, let's do some calculation for these 2 equations, the third one and the 4th equations of the Maxwell equations. First of all, we need to apply divergence theory. This is from the book, your textbook. I try to explain what they are doing. Divergence theory. For the appendix, anyone know what is appendix? Do you know? You know, but appendix, what is appendix? 附录. Okay, you can check there is a part of appendix that talking about vector identity. They have a lot of equations of the vector operators. This is one of it. This is one of it. This equation is value. So if you have a vector A, you apply divergence and you use the integration of this is a volume, integration volume, 体积分. The result will become the vector A and a closed integration of the surface 面积分，这是封闭的面积分。The closed surface integration. You understand? Can you understand this vector identity? This is more. Not only the simple vector operators, but also you apply the calculus on it. There are two integrations. Okay? Usually, this will be discussed in the EM class. This is what we are doing in the EM class. The integration, more complicated. Not only the vector operations, but also calculus. Okay? 我讲那种 sorry for I need to explain a little bit. I think you understand a lot, but they looks like so. 体积分，它积起来一个体积，它会等于这个体积的所有表面积整个再积起来，就这样子。这叫 vector identity， 就是向量公式啊，简单来讲是这样，在附录里面都有。OK， so we apply this one to here. What can we do? Maybe I want a question to ask you later because they are very similar. If I want to apply this one to here, I have this one. So what I'm doing is I try to integral to volume individually. Okay? Still make the equation, right? 两边都做体积分一模一样 identical, totally the same thing. For the left part, the left side and the right side. Okay. But for this part, you can use that one because this equation. So you can transfer this part to this one. Because here. Because if this is not A, this is D. This one will become this one. Okay? For the first equation, anyone has question? For the first equivalent, it's okay, right? This one become this one because vector identity. Okay. And for this part, do you remember this is volume density, the current, the charge density. So you integral according to the volume, it will become Q, the total charge in this area. Are we good? Okay, so what is the result? What is the result? From this equation, you will know that this one will become Q. you have a field, E field, and the E field, and you know what the material is, you can obtain the D, the electric flux density, right? You integrate the surface close to some area, you will know how many charges are in this area. What's that? That is Gauss's law. Have you ever learned this before? No? I integrate any space. I use the closed surface integral to anywhere. You will know the result will equals to the charge inside this space. If there is no charge in this space, this one will equal to 0. This is Gauss's law. You can read that the flux of the electric field, the strength vector through any closed surface in the electrostatic field equals to the total charge caused by the surface divided by epsilon. This is the sentence I copied from Wikipedia. This is from Wiki. This is Gauss's law. So, which means this is Gauss's law. Okay? I try to explain what is this. This is Gauss's law. 你们有没有听过高斯定理？就是 the same. This is Gauss's law. You heard this before. This looks very simple, but by applying the divergence theorem, you will find out that, oh, this is Gauss's law. Okay? Okay? And similar for B, because it equals to 0. This is also Gauss's law. They are both Gauss's law. The electric Gauss's law and the magnetic Gauss's law, both of them. You just integrate the surface and you know what are there, what are in there, how many charges in this closed surface. You should remember it must be closed, OK？ 必须是封闭的表面，它没有封闭就漏掉。Okay, because you have the E field, you have H field, they will have the electrical flux or magnetic flux density. Through all the surface, you integrate all of them, you can obtain how many charges are there. Okay, I think today it's enough for us. Okay. And this week is also introduction, so still not too difficult. If you can catch up, just try harder. Okay. Okay. Any question about this one? 你会不会推 Do you know how to derive? Not so hard, right? Just integral the both sides, and this is Q, and this is the surface. So the closed surface equals to Q, and this is the Gauss's law, and very familiar to everyone. Everyone knows this one. So you can also say the Gauss's law changed to this differential form of the Maxwell equations. We don't know where this comes from, but I just showed it. 好，就下课。OK。